Hello everyone, and welcome to today's presentation. I'm Dr. S.K. Singh, and I'm excited to discuss an important topic with you. Today's focus is on the source of contamination, specifically material outgassing and surface chemistry. Over the next few slides, we'll explore how these factors contribute to contamination issues and what can be done about them. Let's get started. Now, let's take a closer look at the mechanisms of outgassing. First, there's desorption, which is simply molecules leaving the surface of a material. Think of it as particles breaking free and escaping into the surrounding environment. Then, we have diffusion, where gas molecules migrate from the interior bulk of a material up to its surface, gradually making their way out. Next is decomposition, a process where the material itself breaks down, releasing gases in the process. Finally, permeation involves gases passing through a material entirely, moving from one side to the other. Understanding these mechanisms is crucial because contamination control is vital in industries like semiconductor manufacturing, aerospace systems, and pharmaceuticals. Two major hidden sources of contamination are material outgassing and surface chemical interactions. Recognizing how gases escape or interact helps us develop better control strategies, ensuring the integrity and performance of sensitive systems. This knowledge ties directly into our overall goal of maintaining a contaminant-free environment. Let's talk about the factors that influence outgassing. First, temperature plays a significant role. When the temperature goes up, outgassing tends to increase as well. This means that higher temperatures can cause more gases to be released from materials. Next, the type of material itself matters a lot. Polymers, for example, generally outgas more than metals because of their chemical structure. Surface area and porosity are also important. More surface area or porous materials provide more space for trapped gases to escape. Exposure to humidity or solvents can also accelerate outgassing, as moisture or solvents can interact with the material and cause gases to be released. So, what exactly is outgassing? It's the process where gases that are trapped or absorbed inside a material are released over time. This is especially critical in certain environments, like vacuum chambers, or when materials are subjected to high temperatures. Common gases involved include water vapor, which is H2O, hydrocarbons, and gases like carbon monoxide and carbon dioxide. These gases can impact the performance and cleanliness of sensitive systems, making it essential to understand and control outgassing in our designs. Let's take a closer look at some examples of outgassing in different environments. When it comes to spacecraft contamination, one common issue is optical lenses fogging up. This happens because polymers inside the spacecraft release gases, which then settle on the lenses and reduce visibility. It's a clear example of how outgassing can impact sensitive equipment in space. Moving on to semiconductor fabrication, outgassing is also a concern here. Photoresist materials, which are used to create circuit patterns, can release organic compounds as they process. These organics can contaminate the chip surfaces and affect the manufacturing quality. And in vacuum systems, such as those used in scientific research or industrial processes, rubber seals often release water vapor when exposed to vacuum conditions. This outgassing can interfere with experiments or reduce the efficiency of the system. Overall, these examples highlight how outgassing is a common challenge across different fields, and understanding it helps us develop better materials and techniques to minimize contamination and maintain system performance. Now, let's explore surface contamination mechanisms. One key process is adsorption, which is when molecules stick to a surface. This might seem simple, but it plays a big role in contamination and surface reactions. Next, we have chemical reactions like oxidation and hydrolysis. These reactions can alter the surface chemically, leading to corrosion or other changes. Residue formation is also important. Think of thin films that form from airborne contaminants settling on surfaces over time. So, what exactly is surface chemistry? It refers to the chemical reactions that happen right at the material's surface. These reactions influence a lot of critical processes, including adsorption, which we just discussed, as well as corrosion, where materials degrade, and catalytic reactions, which are essential in many industrial applications. Understanding these mechanisms helps us better control surface behavior and improve material performance in various environments. Let's take a closer look at some common examples of surface chemistry contamination. First, oxidation of metals is a classic case. For instance, when iron is exposed to moisture and oxygen, it forms rust, which is essentially iron oxide. This process can weaken materials and affect their performance. Moving on, in the semiconductor industry, silicon wafers often face contamination through native oxide layer growth. This thin layer of silicon dioxide can impact device performance if not properly managed. In the pharmaceutical field, surfaces can be problematic too. Reactive surfaces may cause drug degradation, which is a major concern for medication stability and efficacy. Now, understanding how these surfaces interact is key. We have two main types, physisorption and chemisorption. Physisorption involves weak van der Waals forces. These are relatively easy to break and are reversible. Chemisorption, on the other hand, involves strong chemical bonds, making it more permanent. A good example of chemisorption is oxygen binding to metal surfaces, leading to oxidation. This process illustrates how surface interactions can lead to significant changes, whether it's rust formation or other forms of contamination. Recognizing these interactions helps us develop better control strategies for surface contamination in various industries. Let's take a closer look at some of the measurement techniques we use to understand surface contamination and outgassing. First, there's TGA, or thermogravimetric analysis, which helps us measure changes in mass as a material is heated, giving insight into outgassing behavior. Then, we have mass spectrometry, a powerful tool that identifies and quantifies the gases released during heating, providing detailed chemical information. Another important technique is the quartz crystal microbalance, or QCM, which detects tiny mass changes on a surface by measuring frequency shifts of a vibrating crystal, very sensitive for monitoring thin film deposition or contamination in real time. We also use surface analysis tools like XPS or X-ray photoelectron spectroscopy. XPS allows us to analyze the surface composition and chemical states of elements present, offering a detailed picture of surface chemistry. Now, when we combine these techniques, we get a clearer understanding of the combined effect of outgassing and surface chemistry. Outgassed molecules don't just disappear. They tend to deposit on nearby surfaces, leading to issues like thin film contamination and optical degradation. For example, in space applications, satellite mirrors can lose reflectivity because of this contamination, which impacts their performance. Understanding and monitoring these processes with the right measurement techniques is crucial for maintaining the integrity and functionality of sensitive optical systems in challenging environments. Now, let's look at some key mitigation strategies to address material outgassing and surface contamination. First, material selection is crucial. We want to choose low outgassing materials, such as certain metals and ceramics, because they emit fewer volatile compounds that could compromise our environment or equipment. Next, pretreatment processes play a vital role. Bakeout procedures, for example, involve heating materials in controlled conditions to remove trapped gases before they are used in critical environments. This step significantly reduces the risk of contamination down the line. Additionally, working within cleanroom environments helps maintain strict control over airborne particles and contaminants during assembly and handling. Finally, applying surface coatings, like passivation layers, can protect the material surfaces. These coatings help prevent corrosion and reduce outgassing by creating a stable, inert surface. Altogether, these strategies are fundamental in ensuring the integrity and reliability of our systems, aligning with our overall goal of maintaining a contamination-free environment. Let's wrap up with some key takeaways. Outgassing and surface chemistry are really critical sources of contamination that we need to keep in mind. They don't just sit on the side. They can strongly impact the reliability of our products and how well they perform in real-world conditions. That's why choosing the right materials from the start and implementing proper control methods is absolutely essential. By paying close attention to these factors, we can significantly improve both the longevity and the effectiveness of our designs. Remember, understanding and managing contamination sources like outgassing and surface chemistry is fundamental to achieving the best possible outcomes in our projects. For further support, please don't hesitate to reach out to us. We're here to help with any questions or additional information you might need. Just contact us through the provided channels, and we'll be happy to assist you. And with that, I want to thank you all sincerely for your time and attention today. Your engagement is truly appreciated. Remember, we're here to support you in implementing these concepts effectively. So, thank you once again, and I look forward to connecting with you soon.